I have a friend that enjoys coding and he hasn't stopped talking about a snake recently. He left this file on my computer and dares me to uncover a secret phrase from it. Can you assist? At least, that's what the description is for the Capture the Flag challenge we're gonna work through today. My recent poll on the channel's community page where I asked you about the kind of videos you want to watch had CTFs in the lead for the first few days, so I started working on the script for this video. But not long after, the results of the poll sided with explainers on programming patterns. Since I had already started working on this video, I chose to continue with the video at hand instead of course correcting. So please bear with me, programming videos are on the way. But with that out of the way, today we'll begin with a rather easy challenge from PicoCTF called Weird Snake, which should explain the title of the video and what I said in the beginning. But for those of you that are unaware of PicoCTF, it's a Capture the Flag platform hosted by Carnegie Mellon University and is completely free for you to register and practice their challenges. As stated in the description, the challenge has a text file attached. Opening it reviews these long columns of what seem to be assembly-like instructions. I say assembly-like because these aren't opcode mnemonics that you'd find in a real instruction set like ARM or x86 or even RISC-V. To figure out what the contents of this file mean, we could look for contextual cues. For example, the section marked 9 has a line that says code object listcomp from file snake.py. This is a dead giveaway that the challenge has something to do with a Python source file. The list comp also makes sense in a Python context because it would stand for a list comprehension. But even if there were no dead giveaways of being related to Python, we could try looking up one of these instructions. This would lead us to the page for dis, the Python disassembler, which provides a helpful description for what each instruction does. So let's try to build an intuition for this Python bytecode thing from the ground up. So Python, or more precisely CPython, runs a Python script by compiling it into bytecode and then running it in a virtual machine. Ever notice that weird looking PyCache directory in your Python projects? That's where the compiled bytecode gets stored as .pyc files. That said, we must not confuse this virtual machine with solutions like kvm plus libvirt or VirtualBox. This Python virtual machine is a simple stack machine that executes these bytecode instructions one by one, pushing and popping values on and off the stack as needed to perform these operations. Coming back to the disassembly module, while it can be used to show the disassembly for source files and bytecode, the disassembly is only meant for human consumption and cannot be converted back into code mechanically. There are tools like Python XASM that attempt to solve this, but we have to pass in metadata like the current state of the stack, the constants, etc. to get it working. Given that we don't have access to any of this metadata, we have to take the manual route to make sense of these instructions and reverse engineer them, so let's dive right in. Let's start with the first block comprising a bunch of load const operations. The load const operation indexes into the constants baked into a bytecode file and pushes the retrieved values onto the stack. Although this list of baked-in constants, known as co-consts, is not directly available to us in the disassembly, each line ends with a handy representation of what's being operated on in parentheses. Thus, we can deduce that the first instruction loads the 0th constant from co-const, which happens to be the number 4, and pushes it onto the stack. The program continues this process of loading constants onto the stack for 40 elements in total. This is followed by a build list operation with the operand 40. It instructs the virtual machine to take these 40 elements we just pushed onto the stack, wrapping them in a list and pushing the list back onto the stack. The subsequent store name instruction stores the list away under the variable name input list. Storing a value in a variable pops the value off the stack and binds it with a variable name. Next up, the disassembly loads the string j as a constant and stores it as the variable keystir. Remember, the store name instruction stores a variable away, but right after loading the underscore character, the value of this keystir variable is loaded back onto the stack. With these two strings on the stack, we perform a binary add operation. Now, the order of binary operations is to first use the lower value and then the upper value on the stack. This order becomes especially important with composite data types like strings, since addition means concatenating two strings and reversing the order yields a different string altogether. We see a similar pattern in the next block, except that the order of loading the strings is switched up, meaning instead of prepending characters, we'll append to the key string variable. Similar string additions go on for the next 3 blocks, one append and one prepend. If we're keeping track, the keystir variable now contains a string t_j03. Next, we see the VM load a code object from another address and the string list comp. With the make function instruction right after, the code object is bound to this name and the newly created function is pushed onto the stack. As we stated previously, the name listComp suggests that this is a list comprehension. We then load the value of the keystring variable to grab its iterator that sequentially yields each character in the string. With the function and the iterator on top of the stack, the subsequent call function instruction, calls the function and passes the iterator as an argument. Going down the disassembly, we'll find that these code objects are disassembled separately in their own sections. So for this function, we'll check out the disassembly of the section corresponding to the line 9. This section starts out by building a list. It then loads an identifier named .0 onto the stack. Now, under normal circumstances, variable names beginning with dots are forbidden in Python. The exception being when the bytecode represents function arguments. In the bytecode representation, each regular argument is named as a dot followed by the index of the argument. Meaning the first argument would be named .0, the second would be .1, and so on. With that, we can reason out that we're loading the first argument onto the stack. With the for_iter instruction, each element yielded by the iterator is pushed onto the stack, some operation is performed on it, and it's popped off the stack. If this sounds like a regular for loop to you, well, it is. In fact, the loop body is demarcated both using the text saying 2byte18 in parentheses, as well as the double angle brackets that serve as visual cues. Inside the loop body, the current element is popped off the stack and stored as the variable char. We then load the global function ord onto the stack and load back the value of the character char so that we can feed it as an argument to the ord function. This ord function converts the character into its corresponding Unicode code point. We then append this number to the list we had built earlier. Note that the number 2 denotes the stack element at index 2. The subsequent jump absolute instruction jumps back to the beginning of the loop to repeat this process for the remaining characters. Okay, going back to the main listing, we see that the list created by the list comprehension is stored away as the variable keylist. The next section appears to perform some sort of comparison. Let's take a closer look. The bytecode loads the length function in Python, and it gets called with the keylist as an argument. This results in the length of the list on the stack top. Similarly, we find the length of the input list. With both of these lengths on the stack, we can perform a compare operation which checks if the first operand is less than the second. If true, we continue to the next section. Otherwise, we jump to a distant instruction at byte 162 as inferred from the pop jump if false instruction. To cover all grounds, let's continue down the happy path to the next section. Here, after loading the keylist variable, instead of loading a global function or a code object, we load the extend method associated with this list object. In Python, the extend method requires an iterable argument, and for that we use the same keylist variable. After that, the method is called and obligatory none value is returned, which is promptly discarded by the pop top instruction. With a jump back to byte 134, we realize that anything between byte 134 and here comprises the body of yet another loop. Breaking out of the loop, we come across another list comprehension. We'll examine its disassembly, but before that, let's see what arguments it accepts. After loading the list comprehension on the stack, the bytecode loads the zip function, the input list, and the key list respectively. This zip function, when called, produces an iterator that picks one element from each list and yields a pair every iteration. The following instruction pushes this iterator onto the stack and calls the function. Which function, you might ask? It's the list comprehension that was on the stack top previously. Let us now dive into the disassembly of the second list comprehension. As usual, we build a list for storing the resultant values, load the 0th argument onto the stack, and start a loop. Now remember how the for_iter instruction pushes each element from the iterator onto the stack? Well, if each of these elements is a sequence in and of itself, we can unpack the constituents using the unpack sequence instruction. Here the bytecode instructs the VM to unpack the sequence into 2 elements, pushes them one by one on the stack, and immediately stores them as the variables A and B respectively. With these 2 variables on the stack, we perform a binary XOR on them. A binary XOR, otherwise known as an exclusive OR, is an involuntary function which, in its simplest form, takes 2 bits and outputs a boolean true when both of them are different and false otherwise. Since we're working with numbers, recall that we use the OR function to convert the characters into numbers. The XOR operates on each pair of bits from the binary representation of these numbers. The number resulting from this XOR operation is appended to the final list, which is what gets returned to its caller. Back on the caller side, the resultant list is stored in the variable very creatively named result. In the final section, the bytecode loads an empty string and its join method. And while we are loading these onto the stack, we're not going to immediately use them. We then load the map function, the chur function, and the result list, followed by a call function instruction. This might be a little confusing since there are 3 functions here, but if we look at the number next to the call function instruction, we can figure out what we're actually calling. In our case, this number is 2, so we're calling the function at index 2 of the stack, which happens to be the map. Whatever stack elements are left on top of it gets applied to it as function arguments. In Python, the map function takes in another function and an iterable, and repeatedly performs the same function on each element of the iterator. So, this new iterator created by the map function applies the chur function on each number in the result list to convert it back into a character. To top it all off, we have a finishing call method instruction that calls the join method of the empty string we pushed on the stack earlier. The join method simply joins the characters or strings in a list with the original string as a delimiter. However, since our original string is empty, we just join all the characters back to back. This final string is then stored as a variable result text, and the program ends. No, really, the program ends. Obviously, from what we can infer, it seems to be that the result text is what we need to figure out as the flag for this challenge. So we'll take another run through the broad strokes and recreate the script. Now before I reconstruct the script, why don't you give it a try? With the hard part already dealt with, you should be able to solve the challenge by yourself. This is the last chance to pause because there will be spoilers ahead. First, create a list of these numbers called input list. Next, initialize a variable keystir with the string j. Prepend an underscore, append an O and a 3, and finally prepend a t. Create a list comprehension for each character in keystir and apply the OR function on it. Store the result in keylist. Now, while the keylist is smaller than the input list, extend the keylist with its own elements, essentially duplicating the list onto itself. Once we're done with that, we zip the input and the keylists and create a list comprehension where for each pair A and B, we calculate their binary XOR. This gets stored in a variable called result. Lastly, we map each number in the result with the chur function, joining them back to back with an empty string, and we're done. The only thing we'd need to do in addition to all of this is to print the resulting text to actually see the fruits of our labor. So let's run our script, and just like that, we've captured the flag. Let me know if you like these capture the flag videos. If you're more of the artsy kind, check out my second channel where I show you a time lapse of how I created the thumbnail for this video. Hope you learned something. See you around.